So we have been talking about the vibration problem till now. So let's continue our discussion further. So we had said that the certain properties of the eigenvalue problem that you form in the free vibration case. One is that the finite element, that the eigenvalues or the natural frequencies obtained from the finite element solution are higher than those obtained by the exact solution or the actual ones. This is sometimes referred to as the finite element system being stiffer than the exact one. Okay. So this is some feature of the finite element solution that one has to keep in mind. So why do we have to keep it in mind? Because if I am writing a program and to do the computation of the natural frequencies of a system, which is a very simple extension of what we had been developing till now, okay, then as a benchmark I should test my program for specific problems for which I can construct the exact solution. Okay. For example, the problem that I have been considering here. Okay. And in that case, when I go and use the finite element approximation and get the natural frequencies, I should get the natural frequencies to be higher than that obtained from the exact one, and as my mesh gets refined, they should converge to the exact one from above. Okay. These are certain features which have to be kept in mind. If it does not happen, then something is wrong in the way I have done my programming or in the way I have developed the finite element approximation. Okay. Let's also look at some implementational issues that we had said that here I had taken this example of a 5-node system. Okay. And we had said, let's say that we are taking a linear approximation, piecewise linear approximation. I can again take higher order approximations just like we have done the standard finite element computation. So here so this is my element 1, this is my element 2, element 3, element 4. So just like we did the procedure for the static analysis, here we have to obtain, if you remember, the global matrices K and M. Okay. Fine. So we have to obtain these global matrices from our finite element computation. How do I do it? Again, I will say that, look, what is this? K was, as I had done, 0 to L integral of EA phi I prime phi j prime dx was Kij. And this can now be written again as we had done earlier, this is over L is equal to 1 to, in this case, 4, the number of elements, xl to xl plus 1, okay, Ea phi I prime phi j prime. So again you see that I can break the integral into the sum of the integrals over each of these elements, over the elements. Now which of the phi i's are active in the particular element? The only phi I which is active in this element, let's say element 3, is phi 3 and phi 4. So exactly what we had been doing till now will now be done, and we will compute these matrices, these things at the element level, assemble them in the global matrices, and we are done. But we will have to do for the mass matrix also, where the integral will be integral of rho phi I phi j. Okay. So we have to now compute the element level stiffness and mass matrices. Element level stiffness and mass matrices and mass matrices. How do I go about doing it? Let's see. So we have our generic element with node L plus 1. This is my element IL. Okay. Here the basis function from the figure I have drawn, which is non-zero, the basis functions will be phi L and phi L plus 1. These will correspond to the element level N1 of the element, this will be n2 of the element. Okay. So if I want to write u f ux, the approximation of it in the element IL will be equal to alpha L phi L plus alpha L plus 1 phi L plus 1. You see, now these things won't change, these things remain the same as what we had been doing till now. Okay. So what we are going to do is we are going to essentially find these, the effect of these in the integrals. So we will have integral at the element level xl to xl plus 1 EA ni for the element prime nj for the element L prime dx, prime means the derivative with respect to x. This is equal to kij for the element L. What is this I? I is equal to 1 to 2. In fact, if you use higher order approximation, it goes up to p plus 1, and j is equal to 1 to 2. So this will give me a 2 by 2 matrix in the case of the element. Okay. So this will give me k for the element. Similarly, I will have integral from xl to xl plus 1 rho, okay, ni for the element, nj for the element dx. This is equal to mij for the element L. Okay. Now what is the assembly procedure? Assembly procedure will be this I locally at the element level corresponds to the global something, it will correspond to some global I, and similarly the j at the element level corresponds to some global j. So I equal to 1 corresponds to L, I equal to 2 corresponds to L plus 1 globally, j equal to 1 corresponds to L globally, and j equal to 2 corresponds to L plus 1 globally. That is, I again use the local to global enumeration routine that we had made long ago in the one dimensional code, okay, to give me this information. And then what do? I will go and assemble in the following way: k L L will be equal to, this is at the global level, k L L plus k 1 1 from the element. K L L plus 1 will be equal to k L L plus 1 plus k 1 2 for the element. K L plus 1 L will be k L plus 1 L plus k 2 1 for the element. K L plus 1 L plus 1 will be equal to k L plus 1 L plus 1 plus k 2 2 for the element. So this is the simple assembly procedure for the K matrix. It's exactly the same as what we had done, and similarly we'll do for the mass matrix the assembly, that is M L L is equal to M L L plus M 1 1 L, okay, M L L plus 1 is equal to M L L plus 1 plus M 1 2 L, and M L plus 1 L is equal to M L plus 1 L plus M 2 1 L, and finally M L plus 1 L plus 1 is equal to M L plus 1 comma L plus 1 plus M 2 2 for the element. This is all. So we do this assembly procedure, we loop over all the elements, and we construct the global K and the M matrices. Now the question is that the K and the M, if I take again our problem that we had considered, okay, the mesh that we have taken, this will be a 5 by 5 system, but from the boundary condition at this end I have to put alpha 1 equal to 0, because the ux has to be 0 at the point x equal to 0. So how do I enforce alpha 1 equal to 0? Okay. One way is to actually take the global systems and eliminate alpha 1. Okay. So set alpha 1 equal to 0 from boundary condition, Okay. We can do that, reduce this 5 by 5 system to a 4 by 4 system, that is just remove the variable alpha 1 and the first equation. Okay. So we will actually be solving for the system which will have k22, k23, k24, k25 all the way down to k52, k53, k54, k55. Okay. This into alpha 2, alpha 3, alpha 4, alpha 5. This will be equal to lambda here m22, m23 and so on, m25, m52, m53 and so on up to m55 into alpha. So this will be the reduced system, or we can use the tool that we had developed for doing the elimination, that is we go to the 5 by 5 system. Okay. How did we set alpha equal to 0 on both sides? We will simply eliminate. So we will do this, set this guy to 1, first entry, okay, then make it 0, then I will have k22, k23, k24, k25 and so on into my alpha array. Alpha vector is equal to lambda into, I will put again here 1, 0, 0, 0, 0, 0, 0, 0, 0 and then m22 and so on. Okay. So what this will do is the first row gets completely decoupled and you will get essentially alpha 1 is equal to lambda alpha 1. Okay. This will give me lambda is equal to 1. Okay. So we will get one eigenvalue as 1, throw it out. Okay. We will not consider this eigenvalue in our system of natural frequencies. We will throw all this eigenvalue out, and the remaining eigenvalues, the remaining 4 eigenvalues will be the ones we are going to take. So we will take lambda 2, lambda 3, lambda 4, lambda 5. These will become our modes. Okay. This becomes the first mode, this becomes and so on. So this will actually lead to our omega 1, this will lead to omega 2, this will lead to omega 3 and this will be omega 4. You should check that indeed the eigenvalues are the same as what you would have obtained by doing this. Okay. This or the next one would be equivalent, but throw this eigenvalue out from your set of equations. Okay. So with this we should be in a position to set up the eigenvalue problem and solve it. Okay. One more thing that we would like to talk of is, again, while doing these integrations we go to the master element, use all the tools that we had developed as far as integration over the master element is concerned, do the numerical integrations, create the matrices and you will get a solution. Now let's go back and see what we had done as far as the exact solution is concerned. So we had these functions as our modes corresponding to the natural frequencies omega 1, omega 2, omega 3, omega 4, and we said these modes are oscillatory in nature, and we said keep a note of that because this was needed in what we do. Now you see the first mode shape is like this, second one is like this, third one is like this. Imagine now, let's go back and recreate this picture in what we are doing. Okay. So let's come here. This is x is equal to L, okay, and here is my exact u1 as a function of x corresponding to omega 1. What will my finite element approximation do if I took a one element solution? That is, if I took a mesh with only one element, x equal, this is L, this is 0, I simply put one element. In that case, you will see that you will get a 1 by 1 system, because one element will have the two nodes, this node will be knocked off, you will be only left in terms of this one, and the solution will may look something like this. This will be what you get as u1 Fe, okay, from the finite element solution. It will be a straight line, okay. Now this, as you see, this curve is quite a nice curve, so this won't be such a bad approximation, and you can see that if you solve the one element problem, that is a single degree of freedom problem, you will get an eigenvalue which is very close to the exact one, okay. In fact, we can do it here. I mean, let's do it here. Here, if this is 0, this is L, the first shape function will be essentially this one and this one. This shape function will be x by L, and this one will be 1 minus x by L. So we are only interested in this. So our UFE as a function of x will be equal to alpha x over L. Okay, so integral 0 to L EA, okay, the derivative of x by L, so 1 by L into 1 by L dx is equal to k11. This will be equal to EA by L, okay. Similarly, the mass matrix will be 0 to L rho into x squared by L squared dx. This will be equal to rho by L squared into x cubed by 3, so it will be 1 by 3 L cubed, okay. So this will be equal to rho L by 3. So we get this is M11, okay. Now if I do this problem, I'll get K11 into alpha is equal to lambda M11 into alpha, okay. So implies lambda will be equal to K11 by M11, okay, which will be equal to EA by L, so EA by L, okay, by L divided by rho L by 3. So this will be equal to EA by 3 EA by rho L squared. So lambda will be 3 EA by rho L squared, lambda from the finite element solution, okay. So this is what we'll get for that problem, okay. So once we have this, now what about the alpha, okay. The alpha can now be computed quite easily, but let's look at this lambda. What was the lambda exact? If I go back to my earlier result, lambda exact will be equal to much earlier, okay, it will be essentially the square of this, okay, because if you remember the way we have done, omega squared was our lambda. So let's go to omega, and so it will be 2 into 1 pi by 2L EA by rho, okay. So let's whole squared pi by 2L EA by rho whole squared, okay, that will be pi by 2L into EA by rho whole thing squared. Okay, this will be equal to pi squared by 4, okay, into EA by rho L squared. Okay, so if you see that pi squared will be approximately 10 by 4, so this will be approximately 2.5 approximately, and what you get, so this is approximately 2.5 EA by rho L squared. This is the lambda exact. Okay, now you see that the lambda exact is less than the lambda we have obtained, and the eigenvalue or the natural frequency, the natural frequency will be square root of this. Okay, and you see that this is quite close as an approximation, not bad. With one element we could create a solution which is quite close to the one which we actually needed. Now let's go back and look at the two-term solution if I did. So what will happen if I did a two-term solution? So I put this. So what will happen if I do a two-term solution, that is when I put two elements, you see that this, my approximation of the mode shape, will become better. As this becomes better, I will see that my lambda 1 Fe will come much closer to lambda exact, lambda 1 exact. And further, now you see that if I took this one-term solution, I just cannot expect to do a good job for the second mode. There is no second mode which I could capture. With the two-term solution now, I will have two eigenvalues. That is, two frequencies can seemingly be approximated with the two-term solution. What was my second mode? If you remember, the second mode would do this. Okay. Now with the two-term solution, what I will get for the one mode, very good. For the second mode, I will do, most probably I will do this. Okay. So this is certainly not a very good approximation of the second mode. Okay, but nevertheless it's an approximation, and you will see that when I took a two-element mesh, my lambda 1 Fe will be very close to the lambda 1 that I exact, but the lambda 2 Fe will not be as close as to the lambda 2 exact. Okay, but it will again be higher, not so bad, but badness will be certainly more as compared to the lambda 1. So what we can do is, as we refine the mesh further and further, the quality of the approximation of the natural frequency or the eigenvalue corresponding to this problem becomes better and better. That is, with the mesh size h, the lambda Fe, or in that sense omega Fe, tends to the omega exact. Okay, how fast? So how fast is, there's a very interesting way of measuring it, and that is given by, if you say in this case where we have distinct eigenvalues, lambda I minus, or I would not say, yeah, lambda is fine, minus lambda I due to the finite element solution for a given mesh. I could have 100 elements in the mesh, or I could have 5 elements in the mesh, but as the mesh is refined, that is, as the h changes, okay, I am using the h method or the finite element method, this will be less than equal to some constant into the strain energy of u I exact minus u I Fe. Okay, you see, this is a very important result. This u is the strain energy, which means that this is given by integral 0 to L Ea, okay, into u I exact prime minus u I Fe prime whole squared dx. So this depends on the strain energy of the error. This is called the strain energy of the error in the mode, in the eigen mode, or in the eigen function. Okay, so how well can your finite element method approximate the corresponding mode also reflects on how nicely can you obtain the corresponding frequency. Okay, and you see that this number is dependent on this squared, and here what you see that in the case of the eigenvalue problem, essentially for such a case, lambda I exact minus lambda I, actually I should have it the other way around, but since I've taken the absolute value, it is something C h to the power of 2p. Okay. Now C will change for the corresponding mode, that is as you go higher and higher to the higher and higher frequencies, this constant will degenerate further. Okay, so you will get bigger and bigger error, but the rate of convergence will be this, that is you get twice the rate of convergence of the normal finite element solution. Remember we had talked about the energy norm, that is square root of the strain energy. Here the error in the eigenvalue converges as the strain energy itself. Okay, so eigenvalue problems are much more forgiving as compared to getting information about the pointwise stresses, pointwise strains. Okay, that is you can obtain your eigenmodes with a much coarser mesh. Okay, pretty good values of the eigenvalues or the natural frequencies can come with a much coarser mesh as compared to what will be needed to get pointwise estimation of the stresses and so on. Another issue. Okay, so this is one thing that one should keep in mind, that depending on the particular problem, you have to design the approximation in such a way that you get accurate results, and you should know something more about how the solution behaves. Okay, in order to be confident of what you are computing and what you are giving to the particular user. Okay. Incidentally, this same feature what we had discussed here also works in the two-dimensional problem. That is, let's say I am talking of a domain with a crack domain. Okay, here also I may be interested in solving the elasticity problem. I may be interested in getting the natural frequencies. In that case, what you will get is essentially the solution, the nature of the solution, and how you do the approximation in the vicinity of the crack tip is going to affect the quality of the natural frequencies that you compute for the crack plate. Okay, so the meshing in the vicinity of the crack tip becomes very important. We cannot ignore it, and in fact in this case lambda I exact minus lambda I Fe will go essentially as some constant h to the power of minimum of 2 alpha and p. Okay, that is it depends on whether alpha is small or p is small, and in general the crack leads to where alpha, if you remember, is the exponent of the singular part, leading singular part of the solution. In the case of the crack, it's half, essentially half. Okay, so p, any p you take, it will be certainly greater than half, so alpha will dominate. That is the nature of the singularity at the crack tip is going to dominate your rate of convergence, and then you have to do all the things that we did for the stress computation to get a good solution. Okay, but nevertheless the rate of convergence has the 2 in the power. Okay, so it is certainly better than the pointwise data. Here we are talking of lambda as a global data. Okay, so similarly eigenvalue problems can also be there in the case of buckling. Buckling of plates, beams, etc. Okay. In this case, what happens is that as you take the P against the deflection for a beam, let's say the tip deflection, then where I have, how is the load applied? You see, I have a compressive load being applied to the structure at the center. Okay, this compressive load should lead to only an axial deformation, but there comes a value, if I keep on increasing the load, there comes a value of the load at which the beam or this bar does not deflect in plane, it wants to do this. Okay, so it tries to have a transverse deflection. How do you take care of that? So for that we look at equilibrium in the deformed configuration, and there is a whole theory behind how to do the analysis. Nevertheless, what happens is that as the P increases, this is the transverse deflection, let's say it is of the tip, this increases, there comes a critical value, then it falls. This is essentially what we call as a buckling load or P critical. Okay, and we try to approximate it through, this is solving a nonlinear problem, we try to approximate it using a linearized problem. That is, in the nonlinear problem we use concepts from finite deformation, elasticity and all those things, finite elasticity, but we are not going to use it here. The idealization is based on assuming that up to the critical load the member essentially behaves in a linear elastic way, that is, it is only going to give actual deformations, negative deformations because of the compression. At the critical load it develops transverse deflections also, and without going into the details of it, what we will get is that, let's say that I am applying a load, P is just less than, P is equal to P critical minus a small number, very small number. In that case, equilibrium under the action of the load for this member is governed by standard linear elasticity, that is, I will get integral 0 to L in the energy sense EA, okay, du dx, I am just writing the weak form of the bar problem, dv dx, okay, dx is equal to P into V at L, or minus P into V at L. Okay, this is what drives the problem. Okay, now at the critical load, what will happen if this is up to this point? At this point, I increase this load a little bit so that I get to P critical. Okay, at that point, the strain we had assumed is given by du dx. Not anymore. At this point, the strain will be governed by the nonlinear or the finite strain or the green strain. It will be given as essentially du dx plus, as an approximation, half of dw dx whole square, where w is the transverse deflection. Okay, this is essentially, by throwing out some more higher order terms, this is called the von Karman theory approach. Okay, still you see that you cut anywhere, the axial force is P, and then you can show that you will have, when you increase the load a little bit, this part is assume that I am in equilibrium corresponding to this load. From here I am applying the extra bit, that is, I am applying the extra load to go to the new equilibrium position. The new equilibrium position, given this, will have an additional displacement in the plane and the axial direction and the transverse direction. So this is generally given in terms of what we call as a perturbational displacements from the current equilibrium configuration corresponding to this, and then it can be shown that this whole thing can be written in terms of the following. Weak form, this will be equal to P integral 0 to L, okay, into dwp dx into dw bar p dx. Okay, now the question is, so you see that this essentially gives, if I take now Wp as my incremental or the perturbational transverse deflection. I write it using the finite element representation using the C1 elements. Okay, then this one will be approximated using the finite element way, and this will be the corresponding test function or the weight function. This is again on the right hand side I have the unknown WP, and here is my test function. So this will lead again to an eigenvalue problem of the following type, where K, this is for the bending, into alpha is equal to P into what we call as Kg into alpha. Okay, where is this coming from? This is called the geometric stiffness matrix or the geometric part, in the sense that it is coming from this part of the strain, that is the by representing the large strain components. Okay. Now what will be the entries of K? Kij is equal to integral 0 to L Ei phi I double prime phi j double prime dx, and Kij geometric is equal to integral of 0 to L. Okay, I go back and see what do I have. Phi I prime phi j prime dx. Okay, I am not writing these things in detail. So now again you see that I am really interested in finding this load P at which this happens, at which this transverse deflection is present. Okay, so there again I set up this. Now the phi i's are C1 functions. This is very important that these will be C1. Why? Because we want phi I double prime phi j double prime to be defined. Okay, so we do the same thing again. This is a where my W P as a function of x is given as sum alpha I phi I is equal to 1 to some number of unknowns n. Okay, so this gives me the eigenvalue problem where lambda is equal to P. That is my buckling, that is the load, unknown load, and then the critical load out of this is essentially equal to the minimum eigenvalue that you have. Okay, that's what I am looking at, that I would like to obtain the minimum eigenvalue corresponding to this problem. Okay, so here again I get P critical is equal to the minimum eigenvalue, and how many eigenvalues we will get for this system? We will get n by n, okay, depending on the number of unknowns. Similarly, if I went and solved this in the continuum form, that is, you will get, if you do the formulation of this in an exact form, P this would be the exact differential equation that you have. And again, if you solve using what we had already used for the free vibration problem, I will actually get infinite values of P, because this is an eigenvalue problem at the continuum level. Infinite values of P. There will be distinct values of P, and corresponding to each P I will get a buckled shape, buckled mode shape. Okay, that's exactly what we do in our buckling analysis. And if you see that if I take a rod like this and apply to this a compressive load, how will it deform? It will deform like this. Okay, so the rod will become this at P critical. When the load becomes P critical, the rod will become this. Okay, so as we had talked about earlier, here we have lambda 1, lambda 2 up to lambda n, okay, such that lambda 1 is less than equal to lambda 2 is less than equal to lambda 3 and so on. Okay, so the first eigenvalue is the eigenvalue I am interested in. Now this is very important also from an implementational point of view, because in this analysis we are only interested, most often only interested in the critical load. So I am interested only the first eigenvalue. If I am interested in the first eigenvalue, I really do not need to compute for the remaining eigenvalues. Okay? If I do not need to compute for the remaining eigenvalues, I can use faster solvers which give me the first eigenvalue very nicely. Okay? The cost of computation comes down tremendously if I am interested in only the first few eigenvalues and I am not demanding all the eigenvalues. Okay? So as an implementational issue, computation cost. For the eigenvalue problems, this is a big issue. Okay? This is, and when I want to get information about the first few eigenvalues or one eigenvalue, then the cost comes down tremendously. What will be the accuracy of the p critical that we obtain? Again, it will be determined by essentially this strain energy, the bending strain energy of the perturbational transverse displacement WP. Okay, and how well are we approximating WP? That is, how well is my finite element solution going to represent this mode? Okay, with one element I'll get this. So exactly the same theory. I mean, certainly there are certain differences, but the same ideas can be extended to the eigenvalue problem and their computation. Okay, there are lots of eigenvalue solvers available in the open source. You can download it from the net, or numerical recipes in Fortran and C. There are so many books on those. They also have eigenvalue solvers, which are generally a little bit more difficult to make, program, and make and finally make it useful for computation as compared to the solvers we had for the inversion of the matrices. Okay, so from the open source you can have many such algorithms which are available. You can go to a site called netlib.org. This is an open source site. You can download lots of routines from there. There is something called RPAC, which is a very powerful generalized eigenvalue solver package, available again as a free open source package, which can be used to compute eigenvalues of large systems. You see that here we did not really say what is the size of the system. Depending on the problem, 1D problem, yes, the meshes are small, the approximation is small. When I want to do this eigenvalue problem in 2D or 3D, for example, in the 2D, very important thing is when I am interested in plate buckling. Okay, in this case, the plate is subjected to a compressive load or even to a shear load. Okay, here is my plate subjected to some shear loads. Okay. In that case, I am interested in the critical value of this load. Okay. In that case, if the plate has cutouts everywhere, cracks sitting somewhere at various sites, I have to resolve these geometrical details properly so that my finite element solution corresponding to the buckled mode shape is not bad. Okay, the finite element solution has to be good in order to have a good value of the p critical. Okay, so we have to do the meshing which is fine enough, detailed enough to take care of these details. This leads to a very large sparse eigenvalue problem. The mass matrix and the K and the stiffness matrix could be 20,000, 30,000 or 40,000 by 40,000 in size. Okay, then getting the eigenvalues becomes a tough job, and some of these algorithms have to be used. Okay, there is a very so there's a lot of literature available on how to simply solve a large sparse eigenvalue problem. Okay, which you can use straight away from the literature. Okay, so in this lecture, what we have tried to do is we have tried to cover some classes of eigenvalue problems that arise in mechanics. Okay, some typical examples that we have taken is the vibration problem or the buckling problem, both of which give rise to eigenvalue problems which have to be solved. First they have to be formulated in the finite element sense, and then they have to be solved and then checked whether those numbers are reliable or not. Okay, so benchmark problems have to be solved, and for the students it won't be very difficult to program these in the existing static analysis codes, because you already have the structure with which you have the shape function routines, you have your element calculation routines, where all you have to do is add these extra parts which may be for the computation of the mass matrix or computation of the geometric stiffness matrix, add them. Okay, do follow the same procedure that you were following for the assembly, assemble these matrices, obtain, download or write, whichever way you would like to do, get an eigenvalue solver, put it, check. Okay, so this way we can now expand our codes that we have developed, the 1D and the 2D code, to also take care of eigenvalue problems, and so we can create much more information which is now which is useful to a designer or to an analyst. Okay, so in the next lecture what we are going to do is we are going to look at some problems which fall in the category of nonlinear problems. Till now we have only dealt with linear problems. Okay, what we will do is we will add nonlinearity into the system, which is not forcibly done, but this is where the real situation is. Actually most of the problems in reality, in real life, are nonlinear in nature. Okay, so those nonlinearities, if you add to the system, then what happens to the response of the system in terms of the finite element solution? That is, how do I go ahead and do a finite element computation which will give me the information that I need correctly. Okay, so we are going to look at the finite element formulation for nonlinear problems, and from there we will start. Example could be a very simple example is this. I take a bar, again I stick to our bar that we had. Here is P, here is f of x, and I will now make it lie on elastic supports on either side. Okay, such that the distributed, this can be represented by a distributed spring, okay, axial spring, which can be given with the spring constant kx. We had taken it earlier as k naught. I will add to it a part which is this. So the spring now has a nonlinear part in the definition of the spring constant. Okay, how do I take care of the response of the bar with this kind of a support spring? Example, this could be the effect of a rubbery support, okay, where the rubber behaves in a nonlinear way if you try to find its deformation with respect to the force which is applied. Okay, so this could be a model of a rubbery spring, okay, something like that. We could add more complexities, but primarily we will take this problem as our problem for which we will develop the nonlinear analysis tools. Okay, we will solve the problem and we will see, well, how well or how badly do we do with respect to what is the exact solution of these problems.